Welcome to the lecture on metaprogramming. This will be the second to last one. The next lecture will cover some library features still. That will be the most practical lecture, next one, so keep that in mind. Now for today, what we're going to cover is we're first going to build a system for creating console variables. So if you're familiar with games which have an inbuilt console, right, just think of that, right, where you have variables that you can actually change through some interface, that sort of thing. Then after that, we're just going to cover some more low-level techniques for how metaprograms are built and how you can build your own. Following that, we'll look at a particle system built with metaprogramming, basically entirely in metaprogramming at compile time. And we'll see how far we get into this. Like, depending on time and depending on how fast we go through the first two sections, this one might actually just be pretty much skipped. And then there's exercise. All right. So before we start, one thing I would like to say is that what actually metaprogramming is. So metaprogramming is in general, whenever you're writing code that is intended to generate code. Right? So you're writing code that generates code. And then that code that is generated, you can run at runtime. But metaprogramming happens at compile time. Right, coming in. So, yes?
You need for loops or snippets? Snippets or for loops?
Snippets or for loops? No, like just entire pieces. Like you can generate methods, types, etc. Yeah, so basically stuff you would normally write by hand, you can now let the compiler generate for you. Now this is a fairly advanced topic, so keep that in mind and try to keep up if you can. So, right, what you need is Visual Studio 2017, my contact information as usual. The slides will be made available, so they're probably right after the session. So, and then the same feedback form if anyone wants to give me feedback. I've received one person, so progress. All right, so let's just jump right into it. We're going to start with a system for creating the console variables in games. So, right off the bat, I'm just going to start with what I want this system to do. So, what are the properties I want from the system? How do I want to integrate it into my code, etc., that sort of stuff. So, the first requirement that I want is I want to be able to define this CVar in any source file. So, it doesn't matter which system I'm programming, right? Say I'm working on like some engine stuff or some physics stuff or gameplay stuff, right? I want to be able to put these anywhere in any source file. It's the first requirement. And I also want to be able to put them in header files as a forward declaration, so that you could access them from multiple source files. I want to be able to store and load them to and from a file, and then they must be changeable at runtime. So they're not like some compile time constant, right? They must be able to be loaded dynamically. Finally, they must be any single type. So if I say I want to be able to serialize some of my custom structs, right, that should be possible. And I'm going to make everything global, mainly for the purpose of the slides, fits better. But in general, if you're actually like integrating into some sort of engine, you would generally like branches off of some other object you have access to from pretty much anywhere, right? So then, this is what a file will look like, to make it a bit more concrete. We have categories. So in this case, I say the category color and category window. Then we have some keys. And then after that, we have a bunch of values to those keys. All right? This is kind of like an INI file, right? So you can clearly see, right, colors here have a different type than width and height, for example. Width and height are just numbers. Colors are like a hex literal. Right. So, the way I'm going to design this is with some strategy for architecture design in general, and that's top-down programming. So, the way top-down programming is you first use the system you're trying to build. So you first create the classes that would normally use it, and then after you've actually implemented the usage, that's when you implement the system. So, to start off, this is how I want to be able to define a console variable. And the parameters here, this will be a macro, and the parameters here are, the first one will be a type. After that, the C++ name, so you'll see I can use the C++ name to access the value. Then the stored category, so these are the categories you saw in the INI file. Right? And then the stored name, so this is the key under which it was stored in that INI file. Finally, every CVar will have a default value, so if you have no configuration file, your program will still work just fine, because the default values are inside of the source code. Alright? Now here's a bunch more. So I said these are the window width, height, and scale power. Now scale power is just, it's kind of like upscaling. It's not that important, it's just a number. Right, and then colors, right? The important thing to note here, right, is that this has the color type, and the color type is not a standard type in C++. This is my own type, and I'm making it work with that. Right? Cool. Then moving a little bit on, here we have a game class. Now this is very similar to the NHTV template. So if you've ever used the NHTV template, you can see this as your constructor of the template, and as the parameter of the base class, we're giving it the window, the name of the window, right, the title and the little top bar, and then also the window size and the window scale power. Now you might notice there's a star in front of it, the operator star, and that's the syntax I want to be able to use to access the values of the CVar. So don't think of this as a pointer, right? This will still be our own type, the CVar. It's just I overload this operator to access the values of the CVar. Right? So then, in the update function, I'll first clear the screen, and I'll do this with the background color. So again, I can just access it as if it was a color, right? It is actually a flat color. And similarly, when I draw text, I draw hello world with that color. Right? Any questions? Nope. Great. So moving on. One more thing we need to do is actually start the game. And the way I'll start the game is I'll first load all the CVars from a file. I'll then call game run, which is going to just run the game. And then I'll store the CVars back to the file. Alright? Any questions? Great. So, we wrap all of that in a try-catch just so that errors get printed out to sincere, so the standard error output. Cool. So, let's begin implementing CVar define. That's the key element of our interface. So, we start off with a macro. This is what a macro definition looks like. We do hashtag define, so it's the C preprocessor that does this. And this is the macro parameter list. So we can give a bunch of parameters to a macro. Now, macros are a very C-like system, so it's basically just textual replacement, right? So basically any parameters we stuck in there, whenever we use it, it's like literally as if we had just copied the text and pasted it in there. There's no magic things with types going on here. This is just textual replacement. So what is this thing at the end of the line? Anyone knows? Alright, he says expand next macro to the next line, yes?
And the macro continues to next.
Macro continues to the next line? Alright, so yeah, it's actually nothing specific to macros, it's just a C/C++ thing. If you put a slash at the end of the line, that's basically you're telling the compiler ignore the next new line. So it just puts the next line on the same line. But yes, you use this to have a macro span multiple lines. Cool. Now our macro is actually not that long, so we start off, this will be a variable declaration, or definition actually. So first of all the type, now this is the type I'll be using, console CVar. Now you might notice that there's the two columns at the start. That just means that you're wanting to get something from global scope. Then I put the namespace, and then I put the type in itself. Now the type will be a templated type on the actual type that was passed in, so as the parameter. Right, so if I said, right, I want a CVar of type color, the color will be used as a template parameter. Then we have the variable name, so this is the C++ variable name, through which we can access it. And then we just pass the rest of the parameters onto the constructor of that CVar type that we're going to be creating. So, what are these? Yeah, so he says it makes it into a string. So this is called the stringification. It basically takes any parameter we have and turns it into a string. So when I type window in my CVar define, right, that window literally gets transformed into a C-style string with window in it. So basically for window width, this is what that part would look like. Right? So that's basically macros. There will be a little bit more to it later, but for now, there's also the CVar declare macro, which I'll use to forward the declare macro. So it has the extern keyword. That basically means this macro is, or this variable is defined somewhere else. Right? So you put this in a header file, and it just tells the linker, all right, somewhere else you should be able to find this. and then the type will be the same and the variable name will be the same. Right? So, moving on. Now let's start on the CVar type. So like I said, it's a templated type. It lives in the namespace console, but I'm going to hide the namespace because I need more space on screen. So we started with class CVar. It takes a single template parameter, type name T, and that will be the type of the CVar that we're going to access. So the first thing, we're going to sort a bunch of properties. So we're going to sort a category, the name, and then the default value and the current value. So the current value is actually where we'll be storing the value that we access, and the default value is just whatever we gave it. And similarly, the name and category are also whatever we just gave it. Alright? Then we have a constructor, which looks much more complicated than it actually is. It just takes the category, the name, and then the default value, and it initializes the fields. And you might notice the default value gets copied into both default value and current value. So by default, the variable will have the default value. Makes sense. And then we have the star operator, which I talked about before, right? This just gives us access to the value. So using this, we can actually extract the current value. All right.
Why is the constructor explicit?
Why is the constructor explicit? Because we'll only be creating this type with our own macro. This type is not intended to be just randomly created everywhere. And by making it explicit, you can only create it if you have a fully qualified type. So basically, it forces us to, like if you were to return a console variable from a function, you couldn't use the return type uniform initialization, right? So you couldn't just put like the brackets in the return statement. You'd actually have to put the full type there. So it's mostly just because we don't want the other features that it has, right? If we made it implicit. All right, moving on. One thing we'll need is type erasure, and I'll explain what that is. So CVar of type T is strongly typed. That basically means we know exactly what type we're dealing with. We know we're dealing with an int or with a color, right? It's all the same to us. So these CVar definitions will be loaded at runtime. Right? We're creating these variables. They're static. They're basically global variables, these CVars, and that means they get loaded whenever we do static initialization. So static initialization is the initialization that happens when your program starts up. Right? So your program starts running and it just goes through all your global variables and initializes them one by one. But one thing to note is that the order in which it does that is undefined. So you don't know whether the global variables from one file will be loaded before the global variables from another. Just one thing to keep in mind. Now, we need to be able to act on different types at runtime. So we have this CVar of I32, right, that's just an int, and we have the CVar of color, and we need to be able to act on them as if they were the same type. Right? We can't like use this information at compile time because we don't have the information at compile time. We're defining them in different source files. So there's not one source file which knows of every single CVar that exists. So that's why we need type erasure. Now, if we rephrase this, basically what we want to do is we want to act on different types through a similar interface. And what's the tool for doing that? Anyone knows? Someone said interface class? Yes. Well, what we need is polymorphism. And indeed, one way of getting polymorphism is through virtual inheritance. Right? There are other ways to get polymorphism. I'm not going to talk too much about them, but function pointers are one way. That's the C way of doing things. And then you have this thing, the curiously recurring template pattern, CRTP. That's basically polymorphism at compile time. But as much as I'd like to talk about it, it's a bit outside of the scope, so we're not going to cover it today. Right. And then we can use this polymorphism to get type erasure. And type erasure is like literally what the name says. We're erasing type information. So we had something which actually knew what its type was, and we're changing it to something, in this case a base class, which doesn't know the type anymore. Just knows the interface. So that's why it's called type erasure. All right. So what interface are we going to be using? Well, I'm going to show you all the methods that will be associated with the CVar system here. So the first one will be load CVars. And we take a string view to the source information. So the goal is just, right, we give it a string and tell it, okay, right, parse this string. And I'll add a single parameter to that, which is the load warning function. the warning callback. Basically, anytime during parsing we see something that's like fishy or something that's not correct in the input, we just call this warning callback, and that warning callback can, maybe print it to the user so that they know what went wrong. So that's what the warning callback is for. And the warning callback is a function pointer. So the function returns a void, and it takes a single parameter, string view, for the warning. Right. Everyone understands the function pointers? Cool. Then moving on, we also need a save CVars function. So this one will just return a string. It's just going to, serialize all the CVars into a string that can be saved to the file system. And then we have a reset CVars function. So this one will just reset every CVar to its default value. Right. Then we need a base class. And this base class will have a bunch of functions. So first of all, we create a protected destructor because we don't plan to destroy items through the base class, right? All our CVars will be created during static initialization and will be destroyed during static destruction. So we don't have to have any destruction through the base class, that's why it's protected. Similarly, we then have some virtual methods, which are pure virtual. So that means they have to be implemented by whoever implements this class. So we start off with two functions, serialize and deserialize. Now, serialize is pretty straightforward. It just returns a string from the value. And then deserialize has a bit more to it. Right? On failure, if it fails to deserialize, it will return false. And if it succeeds, it will return true and also set the current value to whatever was deserialized. So that's what deserialize will do. And then we have some public interfaces, and the first one is we have a category and a name, so we're just going to get the string views for those, and then we have the reset function. All right? Any questions about the base class? Yes?
What did the no except keyword do?
The no except keyword tells you that this function should not throw an exception. If a no except function does throw an exception, it will terminate your program. It's like a hard crash.
What is a string view?
What is a string view? So a string view is a non-owning view into a string. It's basically a start pointer to a character array and the length. So you can create a string view from C-style strings, you can create a string view from regular strings, and from a bunch of other things. So they're basically like a lightweight way of passing around a pointer and a size. Right? But they don't own any memory, that's the important part. The reason we can use string views here is simply because we're dealing with global variables and we're passing them C-style strings as parameters. These parameters will always be global, right? So we know that the string never goes out of scope. So then we have in the CVar base, right, we're going to say friend to the load and the save function. Now friend just means that those functions can access members, like the protected members on this class. So they can call the serialize and deserialize function. Right. Then moving on to the CVar, we actually have to implement the base class here. So we mark the class as final. We don't want any more derived classes from this, and we implement detail CVar base. Right? And the first function we have to implement is serialize. So string. Now the actual serialization logic is not in here. It's in this console parser of type T. We'll take a look at this in a second, the next slide actually. So for now, the serialize function just calls some other function. And similarly, the deserialize function also just calls some other function. Right. Then there's the reset function. This one's the simplest. Just sets the current value to default value. The name and the category, also very simple. They just return the category and the name. And then the constructor. There's something more we got to do in here, which is whenever we create a CVar, we want to be able to inform our system that we've created a CVar. So we create this function, register CVar, and it takes a reference to a CVar base, right? And this register CVar, like we'll implement it, and we can then just store it somewhere so that anytime we want to load all the CVars, we have a list of all the CVars that are in our program. So this is just used to get a list of every CVar into it, and we call it from the constructor. So every time we create a CVar, which will be during static initialization, we're calling this register CVar function. Right? Okay. Then moving on to the console parser. This will actually do the parsing logic for serialization and deserialization. So first up, it is a templated class. Right? It knows how to serialize type of T. And the reason we have this at all in the first place is for two reasons. First of all, this allows us to move the code of parsing types out of the CVar class. The CVar class has enough stuff in it, right? It has the name, the category, all that sort of stuff. So we just move it into a different file that makes it easier to work with. And also because it allows for easy specialization. So if you remember template specialization, that's what we'll be doing with the console parser. And we'll see that in a second. But first, the serialize and deserialize functions, they have the same signature, except this time they actually take a type T. And then what we do is we have string stream for serialization. We just create a string stream, we move the input into it, right? So we use the standard IO streams in C++ to do the serialization here. And then we return string stream.string, which generates a string for us. All right? Then for deserialization, it's a bit more code, because we want to make sure that we can actually deserialize it. We don't want any errors. Did you have a question? No, okay. So what we do is we take the string stream again. We push the input into it, right? And then we move the input. We then read from it again into the intermediate variable. And we check if this reading failed. We return false. Otherwise, we assign the output, and we return true. Any questions about this? Yes. Why do I move the input? So std move, I'm just putting it around it, right? If the type is movable, then it will move. We don't longer need intermediate. If the type is not movable, this will do a copy. So for types like int and color, it will just do a copy. But if we could have some faster move operation, it would use that.
What I mean is like we put input back into the string stream, and then we get back onto the reader.
Oh, okay. So why do we first like push input into the string stream and then extract it? That's simply because we want to use the IO streams logic to do the thing. So string stream input is just a string, right? That will always be string. So we're basically just creating a string stream which has the value of that string, and then we're extracting the actual typed value out of it with IO streams. Right? You had a question too? Okay. So that's the interface for this. Now, our colors cannot be used with with IO streams. So instead of that, we'll do a specialization. This is a full or explicit specialization of a template. So basically, what happens here, right? Every time we used to have type T, we now use type framework : color. So the color type actually lives in a different namespace, which you see here. But yeah. So basically, every time we try to parse a color instead of like an int or something, right? It will actually be using this logic instead. So take a look what that looks like. Now for the serialize, we just have this function on the color type actually, which creates a hex string from it. So that's where all the hex logic is in. And then we return that, we create a string from that. And then following that we have deserialize, and this again has a function just on the color type, which will turn a hex string into just a color value. And it actually returns a std optional of type color. Now optional basically means it either has a type or it doesn't have the type, right? That's pretty logical. So we just check, alright, does the parse result have a value? So if the parsing function returned a value, right, then it actually had the value. And if it doesn't return a value, that means the parsing failed. So if this from hex string fails, it will just return nothing, basically, an empty optional, right?
So why do you actually use the, what is it called? Can you go one back? That one. Why do you use the std optional instead of just checking against the null or something? Is it more
so we're not actually, it's not actually, the function doesn't actually return a string or a pointer or something, right? It's not something that can be null on its own. It actually returns just an array of 10 characters. 1 for the hash, 8 for the.
And if it fails to parse,
if it fails to parse, then it returns, yeah. So that's why I use it. Basically, a std optional is just a bool and the value, right? And if the bool is false, you get the value. If the bool is true, you get the value, and if the bool is false, you don't get the value. Right? But optional is a useful technique for whenever you have something that's not a pointer, that should not always be there, right? With pointer, you can say no pointer. With something that's not a pointer, you can't. So that's what this is for. All right. So yeah, this specialization, right? This is full specialization. We're just basically creating a version of console parser for when we have a color. And I hope that's clear. Cool. So then, what we have so far is we have CVar define to define all the console variables. We have CVar base, which is our base class that we use for type erasure. We have console parser of type T, which is the logic for actually turning strings into types and types into strings. And we have a whole bunch of functions we haven't implemented: reset CVar, save CVars, load CVars, and register CVar. And then what we still need to do is, well, obviously implement those, otherwise nothing happens. And we need to load from or to the file system. Right? Cool. So, the register CVar function. Let's start here. So basically what we take here is we take a reference to the CVar base. So we can kind of call all those virtual functions on here, right? But one question I pose to you is, what should we store the CVars in? What would be like an appropriate type to store them in? Someone here said vector. Anyone got something different? All right. Well, I'm just gonna say I'm going to go for a std multimap. We have basically what we have, right? We have these categories, and in each category we have multiple CVar types, and that's what I'm going to use a multimap for, so that I can actually search for the category efficiently. The reason it's not unordered is because we actually want to sort by category. So you might have noticed, but the category color was on top of a window because color comes before window. Right. Now, one thing which is actually quite important, anytime you're dealing with static initialization code, I hinted at it before, but during static initialization, you do not have access to things like global variables. So you can't access anything that's global, and you can't call any functions that depend on things that are global during static initialization, because the order in which things get initialized is undefined. So it might be that you call something, right, that depends on a global variable, but that global variable hasn't been initialized, so it's just random garbage memory, and that's completely undefined. So this is not only something you cannot rely on in theory, this is actually in practice you cannot rely on this, because depending on the order in which your CPP files got built, it might actually be different between runs. So you might have the same program that runs one time successfully and the next time it doesn't run at all. So anytime you're dealing with static initialization, like put a comment in your code or something, you know? Make sure that people know that they can't just access data. So yeah, the data might not be initialized. So if we cannot access global variables, where are we going to store the data? Static function variable. You mean a local static variable inside of a function? Yeah, that's the best trick. So we call a function here, data, and I'll now first of all the map type. I'll show you that. So the data map will be a std multimap from the string view, which will be the categories, to a pointer to the CVar base class. Right? Now here's the data function, and like he said, we're using a static local variable. Now, who except for him knows what that means? Yes? Like a static variable for a class? No, that's not really true. It's a bit different. Yes? Yeah, exactly. So, static variables inside of a function, basically what the compiler will do is it will like put a lot of code around that, so that the first time this function runs, it will initialize this variable, and every other time it basically just skips this line. But you still have access to the variable. Now, the thing about static local variables is that they are not part of the static initialization. Right? They get initialized the first time you call the function. All right? Not the first time, not when the program loads. So one thing to note here is also it is thread safe. So if you're ever doing stuff that actually requires thread safety, it is guaranteed to only ever initialize once, and after that you will always be able to access it. Now, because it also has these thread safety guarantees internally, right, it's not the most efficient thing. So, and sometimes you might be better off not using them. And what we actually do is we assign the result of that to an actual global variable, so that in functions which do not run during static initialization, we can actually skip that step. And we can just straight up access the data map. Right? Cool. So then, now that we have access to a map in which we can store the data, we just extract the name and the category. That's just so that the code becomes shorter. After this, at least, you know, these lines are pretty long. And then the first thing we do is we check if there are any duplicate values. So we use this equal range, which will give us a pair of iterators. They start in an end range, and basically that will just give us every CVar that's already registered in that category. So we can iterate over that with just a for loop, and then we check, all right, is the name the same as the one that's already in this category? Then we just print an error, duplicate CVar, and we throw the error. Now that's basically what this means, is that if you, in two different CPP files, you do CVar define with the same category and name, and maybe a different type or different default value, right? This will just throw an error instead of being random behavior that will likely result in a lot of problems later on. So this just prevents duplicate CVars. And then if there's no duplicates, right, just insert it. Right, any questions about this? I'll give you a second more to look at it. All right, so yeah, moving on. Save CVars. So this is where we're actually going to save all the CVars. First off, we create a string stream, so that's what we're going to be using to just pump all the string data in. And then we get the begin and end iterator of the data map. And then we check, all right, if the data map is empty, then just return an empty string. You know, if there's no CVars in your program, you're not gonna save anything. And then we have a string view current category, and we'll just use this. Remember that the multi-map is ordered, so we know that all the CVars in the same category will be behind each other when we iterate through it. So we can just use current category to see if we switch to a new category. I have to put in a header in there, and you'll see that in a sec. So then we just iterate through all CVars. We check if the category has changed. If the category has changed, right, and we check, right, was the previous category not empty? If so, that means we were already having some keys, so we add an extra new line. Otherwise, what we just do is we print in the square brackets, we print the name of the category. Right? So then moving on, here's where the meat happens, right? So here we're printing a CVar, and what we do is we call CVar.serialize, and by calling that, we get the actual string value that we should print for this CVar. And then we just print the name and the equal sign and the value. And then finally, we return a string from the string stream. Right, any questions? Nope. All right, pretty straightforward. We set CVars. This one's the simplest. For every CVar, call reset. Done. All right. Loading CVars. This one's the trickiest. It's something you'll notice every time you're outputting stuff. It's pretty easy, and then you got to read it back in. That's when stuff gets a bit trickier. So yeah, first we check if the string that we were trying to read is empty. We just do nothing. Then we again keep track of the current category. Then in addition to that, we have the CVar set. I'm not going to really show you the type of this, but it's just an unordered set, so a hedge set that keeps track of a pair of category and name, and that just checks to see if we're reading a file and it has the same category and key defined multiple times in there, we can issue a warning about it. So that's what we use that for. Then we have this weird do loop. Now basically this says just for each line we're going to trim the start of the line, and then so then anything that's not white space at the start of the line will be inside of each line, and then we just iterate over the file like this. I'm not going to show you these exact functions because they're just boilerplate, but basically read this as for each line. So yeah, so it takes the first line from source and it trims the white space from the start. Alright, so then if the line is empty, we ignore it. If the line starts with a hash, I'm going to say that's a comment line, so we ignore it too. Then we're going to see if the first character is a square bracket. That means we're parsing a category. Right? If so, we're trimming the end of the line as well. Then if the last character of the line is something else, something that's not a square bracket. So we opened a square bracket, but we didn't close it. Well, I'm just going to trigger a warning here. And the warning message will be parsed, whatever, you know, but does not end with that. All right. Someone said something? All right. Moving on. So otherwise, we actually extract the category by removing the first bracket and the last bracket, right? So we get a substring, index1, length -2. Pretty straightforward stuff. Then if the category is now empty again, we trigger a warning and we just skip the line. And otherwise we set current category to be the category. Right? So then, now we've parsed categories, now we gotta parse the keys. So index will be the index of the equal sign. So I say everything that comes before the equal sign, that will be our name. Then I check if the index was not found. If there's no equal sign on the line, then we don't understand anything, so we just skip it too. Basically, anytime we do continue, we're just skipping the rest of the line, right? So then we can extract the CVar name. We can again trim the white space from the end. And then we say if the name is empty, well, we're trying to set something that doesn't have a name, so that won't work either. Then if the current category is empty, that means we haven't opened the category yet. Again, a warning and continue. And then prevent duplicate category/name combination. So this is the thing with the map that I had before. It's just going to take the current category and the CVar name, and it's going to check, all right, was this already loaded before? If so, issue a warning, and we just skip it again. So if we have duplicate keys, we're just going to use the first one and ignore the rest. All right, moving on. Search for the category name. So now we're actually like looking through our multimap to find all the CVars with this category. And we create this bool found, which we will set to true if we actually find it. So need some more space for this. We get the CVar, a reference to the CVar. We check if the CVar's name is equal to the CVar name that we found in the file. Right? If so, we set found to true. And here we actually are going to do the work. So we're going to extract the CVar value, and we're going to call deserialize. Now, if deserialize fails, right, again, that's just a warning, and that's the end of it. So then we break. So if we found the CVar name, we know there's no duplicate CVar, so we can just break the loop there. Then one more thing, if we didn't find the CVar, you know, again a warning. So yeah, it's pretty long and pretty ugly. Lots of edge cases, but it will work. So yeah, moving on. File.io, you had a question? No, all right. Okay, file.io. Save CVar to file is actually pretty simple. We create an output file stream to the CVars file, and we just dump save CVars into it. Done. Load file. Well, we first reset all the CVars. That's just because I decided to do that. And then we get an input file stream. We read all of that into a string stream. Then we call load CVars from the string from that. And then here's the more interesting thing, right? That's the warning function. So what is this called? Yeah, it's a lambda function. So it's a lambda function. Now the little square brackets, that's the capture list. We don't have anything in there right now. But basically we take a single parameter, string view, which will be the warning message, and then we just dump the value of that into std.cout, so we can see when there's warn errors with loading the CVar file. All right, that's it. So now, demo time. So here we have a CVars file, and if everything's correct, it should start. Yeah, so it's pretty big. So this is the screen size. Well, let me actually. So the whole point, right, of the CVars is that you can just change the console variables, reload them, and you actually just change these fields. So in this case, like let's say I make it wider, right, and now the window becomes wider. I can also change the colors. So right, and now the color became black for Hello World. I can also reset all the CVars, and then you get the default settings for it. And if I close it, right, and if it says, right, this file has changed, it will save the new variables. All right. So that's how that works. So that's the basic system. Yes.
In your demo, are you update function just checking on
if they're changed? No, I'm pressing a key. Right, that's actually like one of the possible features on here, that you automatically detect when the file has changed and then reload it. But that's you know, That's file.io. I don't like file.io. So, possible extensions, right? One thing we could do is we could add validation on the parameters to make it so that if you put an invalid value into the file, your program doesn't crash and burn, it actually just gives a warning message and uses the default. We can have custom getter setter functions on there. What we could do is we could have events when the stuff changes. And so this is events when we actually change it programmatically, right, when we set a value. And then file system monitoring, which checks if you actually, as a user or as a developer, change the configuration file, and it would automatically reload. That's a bunch of stuff we could add. We're not going to add all of that, but we're going to add one thing, which is validation. So if we start off with the definitions again, right? What we want to do is, for example, we want to set that the window scale power must be at least must be a value between 0 and 3. So here we say, all right, we again use this lambda syntax to create a function, and the function will take a value, and we check if the value is greater than or equal to 0 or less than or equal to 3. All right, and we wrap this in the CVar validate macro. So I'll give you a second to look at that, and then yeah, so the lambda, and we check the condition. So this is basically just checking if the value is valid. So then, let's say we also have this validate size function, which is going to take an I32, and it's going to return if the size is greater than or equal to 128, and we could also stick it in for the other one. Right, so now we have a validation function for the window width and height as well. So we say the window width and height must be at least 128, and the scale power must be between 0 and 3. All right. Is it clear what this is supposed to do to everyone? Cool, then I'm moving on. So basically, to make this happen, CVar define needs to take an optional parameter. So we have a macro that needs to take an optional parameter, and we need to create this CVar validate thing. So let's take a look at that. So in CVar define, what I'm going to be adding is a variadic macro. I spoiled it. Okay, yeah. We're going to turn it into a variadic macro. All right, so we're going to add the triple dots. And that basically means this macro can take any number of arguments. Now note that this has no relation to variadic templates or variadic functions. This is a variadic macro. But they all use the triple dots, so definitely not confusing or anything. And then inside of the actual definitions, we stick this __ VA args. Right? And this will turn into a comma-separated list of arguments. So basically, if we pass in 2 arguments to the macro, these 2 arguments will just be put in here with the comma in between. Again, macros are just textual stuff, right? So it literally just copies and pastes the text in there, right? So then, what are we going to do with the CVar validate? Well, that will take a function as a parameter, and then I'm going to say this is equal to console detail CVar attribute validate. So I'm going to call these attributes, and the one attribute I'm saying is, okay, this is the validation attribute. And then comma, and then the function. Now, again, this is completely textual, so this is like sticking this right into the line above, right? So the CVar attribute validate will just be an empty type that we use to do some function overloading with, which I'll show in a second. But this is what you would call a tag type, a type that doesn't have any content, but we just use it to make the compiler do something different. That's basically one of the techniques from metaprogramming. And then we pass in the function. So if we take a look at this statement, right, the CVar define, I32, window width, and then 128 and the CVar validate, that will basically be transformed into this statement. So we're creating a CVar of type I32 with the name window width, and then to the constructor we pass the string of window and the string of width, and then 128, and then finally we pass these attributes. So the first attribute is validate with the validation function. Right? That's just what the macro will generate for us. Is that clear? Okay. So, moving into the actual implementation of that. So we have the CVar class, and we have the constructor for the CVar class. And now this constructor needs to take any number of parameters. So what can we use for that? What? A variadic thing. What thing? Template, yeah, so a variadic template. So great, variadic template. Lovely. We'll have lots of them. And then we need to also take the attributes. So what is this thing called for anyone who was here last time? Hey, what? It's a parameter pack, but that's not what I meant here. Not really, but close. It's a forwarding reference. So this is a parameter pack of forwarding references. Oh well. And then what we actually are going to do with this, right? We're going to call load attribute, and we're going to forward all these parameters to it. Now load attribute, you can see the name is in green. That means it's something that depends on magic, basically overloading. So first we have this load attribute, which takes no parameters. Right? It's just does nothing. It's like boring. And then we have this one, load attribute, which again takes a very template pack. And the first parameter here will be of that tag type. So if you take a look at this in detail, right, the first parameter is the tag type. So that's just what we say, right, the first parameter must be this tag. Right? And the second parameter is the validation function. Now the validation function will be something that is that returns a bool, a function pointer that returns a bool and takes a single parameter of a reference to a const t. So basically that's why it will take a reference to a const i32 or a reference to a const color or any other type you might put in there. And then the validation function is just going to return true or false depending on, you know, whatever condition you want to check. And then we take the remainder of the arguments, because what we'll do here is we'll set the validate field. So this is a field that we create of validate function. We set that to the value of function. Remember, these are function pointers. And then we call load attribute again with the remainder of the types. So if we were to add multiple attributes here, at some point, right now we only have validation, but if we were to add like event handlers, or we were to add, you know, any other feature that would be custom or optional attributes to the CVars, basically what we can do here is just add more of these overloads, and we can use different tag types to overload between them. And by passing it onwards, then we get we just load each one of them in order. So the first thing I'm going to check for is that function is not a null pointer. If you're trying to say, alright, my validation function should be a null pointer, then you shouldn't have done CVar validate. So then we're going to check that the actual field was a null pointer. Right, the field we have right now must be a null pointer, otherwise that means that somebody tried to pass in multiple validation functions, and that's the whole kind of worm I don't want to get into. So single validation function. If you want to compose the behavior, that's your own job to do that. And then we check, we actually call the validation function on the default value. We want to make sure that whatever default value you gave in must be a valid value. Otherwise, you know, you're kind of screwing with the system here. So that's it. That's how the validation works inside of the CVar object. All right. Now we do need to eventually call this validation function somewhere. So inside of the base class, what we do is we add this extra function validate, and this is just going to check if the value is if the current value is a valid value, and if not, it's going to reset it. So then, if we look into CVar implementing this function, right? If the validate function is null, that means that everything is valid. Or if the validation function is true with a call to the current function, with the current value. So that means basically it validated to true. We're going to return true. Otherwise, we're going to reset the current value to the default value. I'm going to return false. Right? Okay. So moving on. Now during loading, so we had this if CVar.deserialize in there. I know it was a lot of code, so basically this is the part where it deserializes a CVar, right? If it fails to deserialize, if it fails to deserialize, it will just trigger a warning. And if it actually successfully deserializes but fails to validate, it will give a different warning. And that's how the validation is done during loading. That's it. So what we've covered: variadic macros, tag types, static initialization, virtual inheritance and polymorphism to get type erasure, full explicit specialization, function pointers, top-down programming, and yeah, like stuff we can probably improve upon is, right, don't use global variables. That's just a general bad thing to do. I mean, we could probably improve the serialization, like we're currently just using IO streams. That's not ideal. And then we could add a bunch more features. But you know, the slide is already pretty long, so no. All right, then bonus slide, trigger warning. So that's the function you saw during the loading that we got called. And the reason I'm picking this one out is because it's also very template, right? Fun stuff. So here we take a bunch of arguments, again by forwarding reference. We check if the warning function is null. If so, you know, then we don't have to do anything, right? There's no one to listen to our warning, so why even bother? Then we create a string stream, and then we use this weird syntax that you've actually seen before, which is calling a function or an expression on each element of a variadic pack. So basically what we have, right, we're saying to the compiler, all right, create us an initializer list. We're using the comma operator. The comma operator will always return the second operand. Then in the first operand, we're casting the result of that to void. The reason we're doing this is because you can actually overload the comma operator to do something different. So by casting it to void, we're just saying, all right, we don't want this, we don't care about this result. Right, it will still execute, but after casting it to void, right, it will just no longer have a type, so we can't use it anymore. And that avoids it in the case where some class actually overloads the comma operator. I don't know why you'd ever want to do that, but if someone were to actually do that, you know, this is not going to break. And then we have a second parameter 0. So basically we say, right, execute this expression for each element in args. But like, I don't care about the result, I just want a list of zeros here. And we expand the parameter here. And now we get, like, if we were past 5 parameters, we get an initialized list of 5 zeros, which just gets optimized out. All right? Great. And yeah, this is the actual expression that we're doing. So we're doing a string stream, and then we're doing the left shift operator on it. And we are doing std forward with the parameter. So we're just perfect forwarding the parameter to the string stream. So it's basically as if we had written this, you know, literally we just left shift into the string stream all the arguments. Right, and then we trigger the warning function with the string stream string. Yes. Right, any questions about this? Reasonably clear, I hope. All right, then next up, we're actually going to be talking about a bunch of metaprogramming techniques. So this is kind of like the introduction to, you know, what sort of stuff can you do with metaprogramming, and this is more like, yeah, this is the introduction. I mean, it's only been 50 minutes, or 55, so that's actually pretty good. So we might actually reach the third part. So techniques. So type traits. When you're doing metaprogramming, you'll often be working with types, with a lot of types, very complex types sometimes. And you want to manipulate those types, and you want to get information from those types, and that's where type trace comes in. So let's take a look. We have this function add. It's just going to take 2 integers, add them together, return the result. And then we have this alias add pointer, which will be a function pointer to something that returns an int and takes 2 ints. Right? So let's start with the first type trait, is same v. We've actually seen this one before. It checks if 2 types are the same. So I'm going to ask you, is decal type of add the same as add pointer? Is that the same type? Who thinks it is? Like I would say, so you all think it's the same type, right? Such doubt. Okay, who thinks it's not the same type? So, yeah, it's about 50-50 split, right? About just as many people think it's the same type as they think that it's not the same type. Well, it's not the same type, right? If you remember, right, add pointer is a pointer to a function, whereas the decal type of add is just a function type. So the function signature, as someone called it before, is just a function type. So if I were to remove the brackets with a star in there, it would actually be the same type. But then it wouldn't be a pointer anymore. So if we take the address of add, then we get a pointer. Would it be the same type then? Yeah, now more people seem confident now. Yeah, this is definitely the same type. All right. Now we have this another type trait is function, which is going to tell us whether something is a function or not. So is add pointer a function? Okay, anyone thinks yes? No, so everybody seems to be saying no. That's correct. It's not a function. We also have this is function, is pointer. So is add pointer a pointer? Not everyone is completely sure, but yes, it's true. This is only true for like. So there's actually a type of function pointer, member function pointers, and they are not pointers. But that's a different topic. Anyway, is function. Now we get into some new thing, which is to remove pointer t. And remove pointer is actually going to remove a pointer from a type. So if you have a type with a pointer, it's going to remove that pointer. So is this now a function after we remove the pointer? Anyone think to know? Alright, yeah, it's correct. Now it's a function. So we had a pointer to a function, we removed the pointer, now it's just a function type. Right? Then moving on, some array types. So we started with array 1. And array 1 is just going to be an array of 2 elements of int. And we have array 2, which will be 3 elements of array 1. Now I ask you, what is the type of array 2?
Two-dimensional array.
Okay, what are the dimensions?
3 by 2.
Okay, but which order? Which comes first, the 3 or the 2?
3.
So you think the type will be int, and then in brackets 3, and then in brackets 2. Okay. Anyone else? You think the other way around. Alright, well, then you thought wrong. So the actual reason for this is the way that memory is laid out with arrays. Right? If you look at the rightmost dimension, that one is going to be next to each other. So if we want to have an array of 3 array types, so basically like we have an array of arrays, right? What you get is that in order to maintain it, like these 2 elements that you were making an array of are still next to each other, they have to be the rightmost dimension. And that's why it's this way around instead of the other way around. So then we get, array 3, which will be an array of 5 array 2s. Yep. So 5, 3, 2. You get this nice little tree. Alright, then what can we do with this? So we have another type trait, rank. So rank will give us, anyone wants to take a guess? The dimension? Which one of the 3?
The dimension of the base. So I can see this.
Oh, okay, the dimension of the array. Yeah, correct. So this will be for array 1, it will be 1. For array 2, 2. For array 3, it will be 3. Right, 1 dimension, 2 dimensions, 3 dimensions. Alright, now we have extend. What is this going to do? Extend the dimension. So it's going to make more dimensions.
Yeah.
It's not a D, it's like not extending, it's an extent.
We extend up.
Yeah. Yeah. Also, one hint that would have given it away is like you see underscore v, that means it's going to return a value. If it were actually adding some dimension, it would return a type. So it would be underscore t. But that's just, I'm talking about that later actually. But yeah. So what will this do?
Gives you the rank of element 0.
The rank?
No,
The size of the first dimension. Yeah, that's exactly what it does. So for A1, it will be 2. Now this one's of course tricky. What is the first extent of array 2? Is that 3 or is it 2? So who thinks it's 2? 4 people, alright. Who thinks it's 3? The majority. Well, it's 3. Oh. Alright, and then this one should be like pretty similar, right? Then this is the other one, so this is 2. And for array 3, we get 5, 3, 2. Alright. Now, then there's this one, which is underscore t, remove extend. What would that do? So we remove an extend from array 3, what do we get?
Array 2.
Exactly. So we get array 2. We remove an extend from array 2, we get array 1. We remove the extend from array 1, what do we get now? Yeah, int. So yeah, so this is just a way of like turning an array type into a regular type.
And what if we remove extend from int?
You get an int.
We get an int.
No, you get an int. int has, okay, so this is a lot of things you have for type trace. For example, if you do std remove pointer, if the type you give it is not a pointer, it will just give you the original thing. Same if you remove an extend from something that doesn't have any extends, it will just still give you the original thing. Then we have these, remove all extends. It's kind of in the name, right? What will this be? Int. Yeah, like, you know, it's all int. All ints all the way down, right? Now, these are just a few examples. There's like 74 of these. That's too much for me to cover. I recommend you like go to the reference and you just look them up. They're all in the type trace header. So now one thing to note is that this doesn't include aliases. So for each one of these you also have aliases. So if it's talking about a type, you have the name x underscore t with some parameters there. That's basically the same as saying type name x and then the same parameters colon type. And same for underscore v, you get the value. So these are just shorthand ways of writing these type traits. Right? Cool. Then, SFINAE. Anyone ever heard of this? Oh, actually 5 people. That's a lot. No, it's like 7 even. Alright, so SFINAE stands for substitution failure is not an error. And we'll see what that means in a second. So, but this is, in general, this is the bread and butter of metaprogramming. This is what makes stuff work. It's also very weird, but you'll see that as well. So, we have these two structs. The struct which has an x, a field x, and a struct which has a field y. And I've named them has x and has y. And that will not be confusing at all. So, we have this example code here, and in there we're just going to create a has x. And this has x type we're going to use to call this function print xy. So if you look at print xy, I'm going to say that's a function that will print an x or a y on any type. So here what I do is, right, so in this function what I do is I just take a constant reference to an object, and then I do std_out, I print x colon, and then I print the value of x. So I do object.x, right, and then I print a new line. Should be straightforward enough, and can take any type. So now we have hasY. We create it in the example function, and we're calling print xy. So will this work? Who said yes? No? Alright, who said yes? Why? Alright, well, it's not going to work because it's going to try to access x, and it says x is not a member of has y. Right? Yes? Doesn't matter, okay. So then,
Would this be a compile error or would it
yeah, this is a compile error. Like this is literally, like, the actual error would be actually at line 7 because that's where you're trying to access x.
Why would you call a function print xy while you only print x?
Because we're going to change that. But that's a good point, right? At this point, you probably shouldn't be calling it print xy. So now we have another print xy, and all I did was I just changed object.x to object.y and the string x to string y. So right, will this work?
Unambiguous.
You think it's ambiguous? Won't work? Alright. Well, it's not ambiguous. It's just you're trying to create a function template that you've already made, right? These have exactly the same template parameters, exactly the same parameters, exactly the same return type. Compiler doesn't like that. Yes? Yeah, but that's like, that comes later. Yeah, we can enable if that, but that's not actually how we're going to do SFINAE here. We're going to do it without enable if. But yeah, so this won't work. So can we make this work? Well, you already spelled that there's a way to do with enable if, but we're not even going to use enable if. I'm just going to do this. I'm going to add another template parameter on the top, right? It's a type name parameter. It doesn't have a name, right? So the parameter has no name, but it does have a default value of decal type t : x. So we're trying to get the type of whatever x is, right? So let's take a look. What happens when we try to call print xy with has x? Well, can we call this function with that? Who thinks you can? It's like, who thinks you can't? That's only one person. Well, you can. I'm sorry. So okay, so this is what happens, right? T gets deduced to be has x, and then it's going to do the default value on the right hand side, which is has x colon x, which is going to be an int, right? We defined x to be an int, so this will work, right? So it can call print xy with has x and an int as the template parameters, and then it takes that as a reference. Now, will this compile? Right, it can call this, but will this be a compile error or not? No? So who thinks that it's not a compile error? Alright, who thinks it is a compile error? You're correct! It's a compile error! So the problem is, right, in this case, it can also call print xy like the other one, so this time it's an ambiguous overload. So this time it's ambiguous, it doesn't know which one of the two to choose, right? They're both equally good in their eyes. So that's why it's a compile error. We'll fix that later. Let's first look at what happens with print xy. So, can we call this with has y? No. What will happen when we try to? Will it turn it into an x? No. Or an x value? No. Nah. It also has nothing to do with value categories. Okay, so that's pretty damn close to what happens here. So what he said is it tries to access t colon x, right? Has y colon x. Now that doesn't exist, and it will just call another overload. Well, it's pretty close to that. So first type name t gets reduced to has y, and then it's going to do the default value for decal type of t of has y colon x, right? And normally decal type has y colon x would be an error. Your compiler would stop here, right? You get a compile error. You have a question? Okay, so this would normally be a compile error, but if you look at what the name of SFINAE actually is, right? Substitution failure is not an error, so it's trying to substitute this x for has y. Now that's failing, and basically substitution failure is not an error. So instead of giving a compile error here, what it just does is it says, all right, this overload, just discard it. You cannot call it, but it's like, don't consider it to exist at all. Right, so it's just going to pretend like this function doesn't even exist. So no, we can't call this, and then we can call this one just fine. So print xy actually now completely works for anything that does not have an x, which is the other way around, right? So how can we fix that? So now if we look at the bottom right, this will call void of has y, right? That's completely fine. So what if we just add type name decal type t colon y? Now we basically do the same trick to only get elements with y in there for the second overload. Right. Problem solved, right? If an object now has an x and a y, it doesn't work. Yes, but if an object has an x and a y, I don't care. Alright, so that's not the problem. Alright, but will this work otherwise, other than that? Who thinks this will work? Okay, who thinks this won't work? You're correct! So, so the function template has already been defined. We have two functions here. They have exactly the same types in the parameter list. They have exactly the same template types, and they have exactly the same return type. So it's like, you're just giving me two of the same signature here, and the compiler doesn't like that. So how do we fix that? It's actually like, if you see it, you're like, yeah.
Did you use not equal to text value in the second function?
Nope. Now what you just do is you just stick another parameter in there. Done. So this is just a parameter, right? It's a type name parameter. It doesn't even have a name. We just say, okay, it's void. And now at the bottom, yeah?
So if I want to do this with three values, I would go like type name void, type name void.
Yes, if you were to use this method. We're actually going to look at enable if, and then you don't have to. Yeah, you had a question?
That looks very much like very bad practice. Somehow.
This looks like very bad practice. Well,
Type name void is
well,
very ugly.
okay. Here's a life lesson for you. Metaprogramming is very ugly. Like, so you'll see this trick a lot whenever you're doing SFINAE, where you just stick an extra parameter, usually for different reasons. We can actually avoid it here, and that's like the next slide, I believe, or the one after.
You can like create a macro that says like, right, give the template argument ID in a 1, 2, 3, 4.
No, because you cannot do recursion with macros. So, anyway, yeah, so now at the bottom line it actually calls print xy with hasy and void because it added a parameter. So then x will just call, print xy has x comma int, right? And then, yeah, that's basically it. That's how it does this stuff. Not the prettiest code, but it works. So, we could have also used std size t equals size of t colon x, The decal type is not special here. We just wanted something that triggers a compile error and would still be valid if the member is missing. So decal type is not special here. It's just we wanted there to be a compile error if we didn't have an x. So that's why we used decal type, but we could have used size of. Right? So enable if. This is basically your tool for using SFINAE. So as you saw SFINAE on the last slide, right? That's pretty dirty. Like that's not code you really want to be writing. It's very unreadable. Like unless people really know SFINAE very well, they're gonna be like, "What the hell are you doing here?" Decal type of t colon x. All right. Well, that's where you have enable if. So we start off with this example, and we're creating a default random engine. Now, if you've never used the random header in C++, this is basically something you get random numbers from. And you usually use it with a distribution to get the actual random numbers. So what I want to do here is I want to create this function called random number, and I call it with engine and 0. So, all right, now I give it 2 floats, so I want the random number to also be a float, right? Then I call it with 2 ints, and I want the random number to also be an int. And then I also want to be able to call it with an actual template type parameter where I just say, okay, I don't care what I give you, I always want a float, right? And then I can do the same thing for double or unsigned in, etc. Right? So I want this random number to just give me whatever type I give it or deduce the type. One of those. Then I have a bunch of static asserts, which is same, which is just going to check that my code actually worked. So that's just something if you actually want to make sure that your template code works, static asserts are great for that. So let's take a look at random number. So here we started with type name parameter t. So this can just be any type we pass in, and this will be the minimum value, the maximum value, and the return type, because we have this weird thing here. Anyone knows what this is? Nobody's ever seen the syntax? So function forwarding, no, actually. It's not forcing auto, but it's basically just a way to put the return type after function instead of it, in front of it. It's basically just like a syntax trick. It has some more features, but this is called a trailing return type. This has nothing to do with type deduction. The only reason that you stick auto in front is because they needed to use a keyword that wasn't already well, actually auto has a use when you stick it in front of a function, but they just wanted to use a keyword that wouldn't conflict with somebody's function name. So that's why they reused the keyword auto. Yeah, they're very good at reusing keyword. Just wait until they find a use for restrict.
Why not just use t?
Why not just stick t in front? Yes, you could have. So why not? So in this case, we could literally just stick t instead of auto, right? That would be literally the same. But there's a reason I didn't do it. This fits better on slides. So we'll see that in a sec. Yes, this will fit better on slides. Not yet, but you'll see. And also, it was a good place for me to introduce the syntax, because the syntax is going to be used in more places. So it's just I need people to understand that this is just a different place to put the return type. So right, what is this called? Not R value reference, and I heard 2 people said forwarding reference, and then not an R value reference. No, well it is a forwarding reference. So an R value reference to the deduce type. Again, got to keep that in there, right? So, all right, now let's implement it. It's actually pretty trivial. We just say std uniform real distribution of type t. We have a min and a max value, and we call it with engine, right? And then what we get is Well, then what we get is just a random floating point number in that range. Now, there's one problem. This will only work if we have floating points. Uniform real distribution only works for floating points. And we want to use integers as well. So what can we do? Ask them to float. That does not sound like a good idea. Like you're like trying to do a long one. Yeah, you could use SFINAE. Exactly, and in this case, because this is the slide on enable if, right? We stick enable if in there, and this is why it fits better on slides. So enable if, that's this thing. Now enable if, it's a template, and it takes two template parameters. The first one is the condition, and the second one is basically the type if the condition is true. So enable if, what it does, if you give it a true value, a value that evaluates to true, it will give you the type. And if you give it something that will evaluate to false, then it will just give a compile error, and as a result of that, it will disable, right? It will disable the overload. So in this case, because we're using enable if here, right? Basically, you can read this as we enable this overload only when is function point. I think that's actually a typo in the slides. It should be is function point. No, it's floating point. Oh, yeah, I'm just blind. I can't read. Can't read my own slide, right? So basically, if it's a floating point that we're passing in for type T, then we enable this overload. And in any other case, right, this overload does not exist. So, of course, if we have that, right, we also need an overload for handling int types. So it's basically copy paste. The only things I've changed are it now uses a uniform int distribution of type T, and enable is changed to is integral. So we're basically, okay, saying the bottom function works with integral types. Those are things like ints, chars, longs, shorts, all that sort of stuff, right? Things that are integer-like. So if we have that, then we call it with uniform int distribution. Otherwise, we call it with uniform real distribution. All right. Any questions? Yes.
Maybe a stupid question, but all SCD class types and stuff are real SCD things, because I've never heard of the default random engine.
Yeah, all these things are like, so the default random engine, that's in the random header, and uniform real distribution, that's also in the random header, and then like all the enable if is integral, that sort of stuff, that's all in the type trace header. Yeah. All right. So yeah, basically enable if enables an overload if a condition is met. Now it also works for parser specializations, and we'll see that in a second. But first, let's look at how we could actually write enable if ourselves. Because right now it's probably this mystical concept, but it's actually fairly trivial. So let's take a look. We start off with this. We have a function, a class, enable if, and it has template parameters. The first one is a Boolean condition, and the second one is return type, which I'm going to default to void. So if people don't specify a second parameter, that's just going to be void. Right? And inside of this struct, we literally put nothing. It's just an empty struct. Because now we're going to use specialization for when the actual thing is true. So in this case, what we see here, we say, okay, if we have an enable if, where the first condition is true, and the second parameter is any type, I don't care what type it is, right? It will deduce the type. Then this one will match. And if that is true, right? So what is this called specifically? What is this syntax when you're doing this? What is that called? Yeah, exactly. So that's a partial specialization. All right? And when the partial specialization is met, so that basically means the first parameter is true and the second parameter can be any type, then it's just going to have a public alias, type equals return type. All right? So if I rephrase this, right? If the condition is true, it will match the partial specialization, and it will have a public alias type which holds the return value you passed in. Now, that also means, alright, first of all, like in the standard, they also define this alias, enable if underscore t, which is what I actually used on the last slide. This is just an alias, right? It takes the same template parameters, the same defaults, etc., and I just passed it on to enable if. So this is just a way to prevent you from having to type name and then enable if and then colon type at the end. This is just a shorthand syntax. But it also means that if the condition is false, if you attempt to access type on it, you get a compile error. And when you get the compile error, right, you then get SFINAE, which says, alright, it's not an error, and it just disables the overload or partial specialization. Now, partial specializations are very important. We'll have lots of them. So I hope you can understand this. But, yes.
Why is this partial if you looks to me like a full specialization?
Okay, so the difference between a partial and a full specialization. Full specialization is if you provide an exact value for every single parameter. Now in this case we have return type, which is being deduced. And so anytime you have in your template before your specialization, you have any parameters, then you have a partial specialization. Make sense now? Alright, any other questions? Okay, then I'm just going to move on. So one more thing, I believe this is the last slide before the break, is writing your own traits. So we have again these hasX and hasY structs. Now we might want to write our own traits, which I've conveniently called exactly the same. It's unfortunate. Has_x and has_y. And these should be like a variable that I can know at compile time, a boolean, that's going to tell me whether a class has an x or has a y. Yes? No, it's supposed, because I'm checking if it's false.
Yeah.
There's the negation from it. I want it to be false for hasY because hasY doesn't have an x.
Yeah.
Okay? Cool. Then let's take a look at how we can implement hasX. So we start off. It takes a single type name parameter t, and we say, right, by default, the primary template will just say false. So if we get anything, we'll just say false for this. Now, of course, this will compile for the second for hasY, but it won't compile for hasX. So we actually need to check if hasX actually has an x. All right. So then we create a partial specialization. And this partial specialization will take any type name t, and it will match for any type t. And it will say true. Now, this is a bit of a problem because this partial specialization will now match for literally any type. So this will do absolutely nothing. It will just always return true. So what we can do is we can add an extra type name void on the top so that we get an extra parameter to work with type deduction. And this is again something, you'll see this more often with specializations, that you just add a parameter just for SFINAE purposes. And what we can then do, right, so now if we look at hasY, this is calling hasY, void. Right, and similarly it's calling hasX with hasY, void. And similarly, like for hasX, of course, it does the same. So now we get this extra parameter in which we can do some work, some SFINAE work. So in this case, I say, right, decal type t::x as the second parameter. Now that means that for hasY, right, this will fail. So will this work in total? You're going to say yes. Who else thinks this works? Well, a few more people. Okay, who thinks it doesn't work? That's like 2 people for each. I don't know, like, there's a bit more people who don't think it works. I'll give you some more time to think about it. Anyone feeling confident? Yes? Won't work. Why?
Because they both still get go to the first template.
And that happens because?
Because they both the function of my binary is still validate in the template 5.4. They don't go to something like that.
I mean, partial specializations are always matched before the primary template. The primary template is like, if nothing else matches, it will use the primary template. So the point is?
So it doesn't go to it doesn't try to go to the second.
Well, it will always try that first because it's specialization. So specializations always come first. Okay. I'm actually going to.
That's not going to work because SY will also go there.
Yeah. Okay. hasY. Right? Okay. You.
Maybe it's not going to work because for the second type, so both could be
Or for equal class. No, that's also not true. So okay, so let me walk through it. So if we look at has_y, if we try to call this, right? It's first going to try to match the specialization. And that will fail because we do decal type t : x. And decal type t : x, right? X does not exist, so that will give an error. And this partial specialization will SFINAE out. So it's like this doesn't exist. So then the only thing left is a primary template. So for has_y, it will return false. Now for has_x, it will try to match the partial specialization. And it will successfully do decal type t : x. But t : x, right, has type int. And then the decal type of that will be int. So now it has type t, which will be has_x. And the second parameter will be int. And what we gave it was actually t, void. So the SFINAE will work, right? So decal type t, that is x. But because it's x, right, the SFINAE part works, but the partial specialization just doesn't match. Because we expected a void, and we didn't get a void. Right? So basically all we have to do is, there's this another type trait, void t, which takes any number of types, and it just turns them all into a single void. And now it works. Right? Was that followable? Yes. It has to be, okay, so it has to be void because the default parameter for the second one is void. So the template gets instantiated based solely on the primary template's parameter. So the primary template says, okay, I have type name t, which I fill in with has_x. And the second parameter, which type name, which doesn't have a name, I just say that equals to void. So as long as I don't provide it, that's going to be void. So that's why, if I go back here, right, the bottom line here, right, this would actually call has_x with the parameters has_y, comma, void. Because the void is the default value there. Right? Does it make sense now? A bit. Alright. That's more than nothing. Alright, so now I'm going to write another trait, or I'll show you how to, which is going to check if it has an x, and if that x is of a specific type. So here we do, right, has_x of, has_x, and then int, so that should be true. And then if we say does it have an x of float, that should be false, right? And like with has_y, it should always be false because it doesn't even have an x, right? So that's what we're going to try now. So again, we start with the primary template. This time we take two template parameters. First is the type we want to check on, and the second is what we want the type of x to be, right? And we're again just going to set the default to false. So now we're going to do a specialization, which will have as first parameter, right, just t, and a second one it will have decal type of t : x. So right, does this work? I'll give you some more time. Anyone feeling confident? It should return true if it has an x and the x is of the type that we gave it. So in the first case int, in the second case float. You think it will always return if it has an x? Think about it again. Like, what is decal type of t : x? That's going to be an int, right? And an int will only, like the SFINAE part, right? The SFINAE part is the same. It works, right? For anything that doesn't have an x, right, it will always be false. So that part is correct. The thing is, in this case, right, we take the decal type of t : x, right, which will be an int. So this partial specialization will only match if the parameters we gave it were has_x with int. And if it doesn't match, then it just falls back on the primary template. That's how we can write these traits. Alright?
So this would also work if you were to change the struct of has_x to float and then...
Yeah. So if I change the struct to has_x of float, then it would basically return true if you ask has_x of has_x with float, and we return false for the has_x of has_x with int.
How would it match that if it's
How would it match? So that's based on the decal type, right? The decal type retrieves this type of the.
If you do decal type tx, then it would return the type the struct has. Correct?
If we do no, so okay, t is the struct has x.
Yes.
So when we do decal type t : x, we're asking for the thing on x, on type x.
Yeah, that would return an int.
That would indeed return an int. But if we change the struct to have a float x, then it would return a float. Does this make sense now?
Yeah.
Great. And I'm gonna see. Right, so yeah, the new thing here is basically you can use SFINAE in a partial specialization's type deduction. Now, to be clear, that's talking about this part. You can use SFINAE here. That means you cannot use SFINAE here or here, right? Only here. So anytime you're relying on SFINAE, if you do something that has an error on one of the other two places, that will just be a regular compile error. So SFINAE only occurs in like very specific places, right? And now, let's see how much time I have. Not a whole lot. I might just skip this thing. I'm actually just going to skip to the end of this. Ignore the code. I'm just going to like say what policy-based design is. It's basically anytime you have a template parameter that changes the behavior of a class. And some examples in the standard library are anytime you have allocators, like for example subvector takes an allocator as a template parameter. By giving it an allocator yourself, you're actually changing the behavior that subvector works. Similarly, you have unique pointer, which has a custom deleter. You have stud unordered map, which has a hashing function and an equality function. You have stud map, which has a comparison function, a less function, right? So all these sort of things, you can actually pass in your own versions of them. And anytime you have these template parameters you can pass in to change the behavior of a type, those are called policy-based design. So that's just what policy-based design is. You can Google it if you want to know more, or just look at the slides later, but I'm going to skip it for time's sake. So then, type list. So, now that we've actually seen like you can do a bunch of stuff with types, I'm actually going to show you like at compile time you can actually do quite a lot more with types than you thought you could. You can do like, you can basically do any algorithm you want at compile time. It's just, it gets a lot more complicated. So, type list here is just a struct. It takes any number of types as a variadic template parameter, right? And it's just an empty struct. So this is purely something we use at compile time to do stuff with, right? So the first thing I want to show you is to create a type called concat typelist here. And this concat typelist is going to take two typelists as parameters. So this typelist and this typelist. And then the result of that should be a typelist with all the types concatenated to each other. And so this is like a compile time operation that you do, where you take two typelists and combine them into a single typelist. And that's why I'm putting this in stud SFINAE, right, to check if those types should be the same. It's basically my unit test for the code, right? Everyone sees what the goal is? Cool. So, how do we actually write something like this?
That two slides back, you had something with the integers.
The integers and the floats?
I think it's
What?
extend.
Extend, yeah.
And something similar to this.
Yeah, but we gotta write it ourselves. Yeah, this is basically like, we're doing a similar thing, right? Like remove all extends or any of those type traits, except that we're going to write them ourselves. And that's then they work with this typelist type that we created. So, I'm gonna start off. It's obviously going to be something with templates, because always templates. That's metaprogramming for you. How many template parameters should it take? Right, we said 2. Anyone else? Infinite? No. 2. 2. We're taking 2 types, namely the type list. The type lists have infinite parameters themselves, but we're only taking 2 types. So, type name typelist A and typelist B. Alright? And what information do we want to extract from these? Yeah, the types that are actually stored in them. So, the way you can do that, right, they're parameter packs, that's what we want to get access to. And basically the way you can get a parameter pack is through... What did she say? Sorry, I didn't hear.
The STD type, it probably has a function for it.
Nope. You wish. That's not how easy it is. Yes? Tuple? No. That would be like way overkill. And then you still have the same problem because then you have a tuple type which has a parameter pack inside of it.
The expansion, combination with the comma operator and
But it can't be called, like, or typeless is an empty thing. But it's pretty close, because, yeah?
recursion.
Not even recursion. Nice try. The recursion is when you already have a parameter pack and want to do something with it, then it's very useful, but we don't even have the parameter pack, we just have the types. So, the actual answer is type deduction. Type deduction can extract a parameter pack. And there's basically two places we can get this type deduction, either with function calls or with partial specializations. I'm going to show them both. So, yay. Alright, now we cannot specialize an alias, right? Aliases cannot be specialized. As a result, we will need some dummy type, which I'm going to call concat typelist impl, which stands for implementation, which is just going to be the dummy type that is going to do this concatenation. Right, so this is just being forwarded to some class which will take care of it. Right? Cool. So then, we start off, we have this concat typelist impl, and it has, again, two type name parameters, but I haven't given them names because this struct is just an incomplete type. We're not actually using this, we're just interested in the specialization. So what we do is we create a specialization. And here, what we specialize on, right, we take two template type name parameter packs. So this time we actually have two parameter packs inside of a template. Right? You might be like, how can you possibly have two infinite lists after each other? Well, you can't, but the compiler can. And that's what type deduction does. Because then we say, alright, the first parameter has to be a type list of these types in the first type list, right? And the second parameter has to be a type list of TBs. So we're basically now extracting these variadic packs from the type lists. Any questions? Alright. Now, the actual implementation then becomes pretty trivial. We now have two template packs, and we just expand the first one, expand the second one, and we have our type list. Right. Make sense? Okay. Anybody confused by this? No, a few people. Any questions to clarify? How does the compiler do it? Well, this is like just a rule of the compiler when doing type deduction, that when you have a type which has a variadic pack and you're trying to deduce the variadic pack, it can do that. So, basically, in a nutshell, compiler magic. Like, more I can't really say. You know, if you want to know the exact algorithm, it's out there. It's just not very pleasant to read. That's the most stuff with the standard Ds. So, yeah, so this is basically like, this now works. Right, and then, yes?
What happens if you put the same type lists?
What happens if you put, that's no problem, it just works the same. So if you were to put like two type lists which are the same in there,
They will be of the same type.
yeah, which is no problem. Like, if you have one template parameter and pass two different types to it, that would be a problem, but we have two template parameters. So if you have two template parameters, you can pass different types, but also the same types. And it doesn't care. So if we were to have like typeless bool and typeless bool for both parameters, then it would just return a typeless bool. Right? Alright, so let's take a look at another way we can implement this, which with function type deduction. So here what we say is we have this function concat typelist. Right, and again it takes two template parameters, TA and TB. And as a parameter, it has a type list of TAs and a type list of TBs, right? And then we have the auto return type, but actually it's just a training return type. So what we put there is we say we're going to return a type list of TAs, comma TBs, expanding both of them. Right, so if we would call this function, right, with two type lists, it would actually return us a type list which has both types, which has the types concatenated in there, right? Then it just returns an instance of that, right? It's a function, so it has a return value, so it should have a return statement. Now again, instances of type list, right? The type list is an empty struct, so you can create instance of it, right? It will still be an empty instance. So then if we actually take a look at the concat type list, because this is just the implementation, right? If we take a look at this, right? What should we put in here? Yes? Yeah, decal type with the function. Well, with the function call, with the call to the function. That's completely correct. So we put decal type, and then we call the function with two parameters, right? So we create an instance of TA, so of the type list that we were first provided. We create an instance of TB. We pass it to concat type list, and then we take the result of concat type list, which will be the return type. We take the decal type of that, and then we have this type list TAs, TBs. Now, anything in a decal type is not actually executed, so when I say we create an instance of TA, I'm just saying we're pretending to create an instance of TA. We're not actually creating any instances. Right? And that's also the implementation done. Right? Makes sense? Maybe? Alright. Now we want to create another one of these things, another operation we can do on types. So here we have index types. And first parameter we give it an index, and the second parameter we give it a bunch of types, and then what we want is we want it to return that index of the types in our list. Right? So we're basically just trying to index a variadic list of types. So how we write this? Yeah, that's exactly correct. So this time we can use recursion. Great. So we start off with this template. Again, we're dealing with we want to use some specialization here for when the index becomes 0. And because you cannot specialize aliases, right, we need to use some implementation structure here. So the struct index types impl. It takes an index, the first parameter of the type list, and then the remaining parameters of the type list. Or of the, yeah. So then, first of all, the first thing I do is I do a static assert, which makes sure that if you have a type list of 3 elements and you're asking for like the 9th element, right, that should be a compile error. So that's just some error checking there. Otherwise, what I do is I say using type becomes a recursive call to itself. So it's going to call itself again, right? It's going to look into its own index types impl. And this time it does parameter index -1, and it uses the remainder of the types. So we already had the first type here separate. So the first type in that list is a separate thing. And the remainder will simply be basically like any types in the list except for the first one. Right? And now we need a specialization. And specialization, right, it takes, again, a first and remainder. And in the specialization, the first parameter, the index needs to be 0. So we say, okay, when we have index 0, then we know it's the last element, it's actually the element we want, right? And we just say type becomes first. And that's the full implementation. All right. I'm going to be moving on. Now we want to have this thing contains type, where I want to say, all right, the first parameter is the type I want to search for. So I say here int, and I give a bunch of types, and this is the list I want to search in. So basically, for the first case, it says, yes, this list has an int. Right, so we're searching for the int in that list. Now for the second case, we have short is what we're searching for. Again, the same list. And this time it says, no, false. There's no short in the list you gave me. Right. So what is the primary difference? What's like very different from what we've seen before?
Well, in the previous example, then just checking if the first thing is a number 0, and if it's the number 0, then we return the first element.
Mm-hmm.
So that basically we can understand. Now we need to check every line it's the same.
Now we need to check like every element. Is that what
Yeah.
you mean? Right, well, that's not actually what I was hinting at. The thing I was hinting at is that now we're talking about a value. Contains type as a boolean, whereas before we were actually talking about a type, right? We were creating a type list. But yeah, that's also a difference. But again, we're going to do something similar. So contains type will be of type bool. It won't be an actual type itself. So let's take a look at the implementation. So luckily you can specialize variable templates, so we don't need to use this implementation class thing. We can just directly do the specialization here. And contains type will by default be false. So we have type name t, and then we have a bunch of types. And that's the list we're going to check. Now, we'll need a couple of specializations. Anyone knows what specializations we'll need to implement this? Yes?
Usually one where you have two default parameters, so type name T and type name between them, so then the rest.
None of rest. Alright. But
Also one where the type is actually equal to the first type.
yeah, that's completely correct. So we'll need two specializations. This is the first one, which is when the first two types are equal to each other. So if we have a contains type where the type we're looking for is the same as the first type in that list, right, then it's just going to be true. Right? Because that means we already have, like, it's the first element, right? It's there. And then we also need a specialization for if that's not the case, but we still have items in the list. And what we have here is when the first type is type name T and the other type is type name J, so that's some other type, right? What we're just going to do is we're going to call ourselves recursively. So again, we'll use recursion to figure out if this item is in the type. Now if we take a look at how this actually expands, so here we have contains type, int float double int void, right? Which specialization is going to match, if any? Like which of the three is it going to use? The bottom one, yeah. So it's going to use the bottom one, and that basically means, right, now we're basically calling to contains type int double int void. And which one is this going to match? Again, the bottom one, right? And now we have contains type int void. Which one's this going to match? Yeah, the middle one. So now it matches the middle one, and the middle one is just true, so it's true. You see how this works? Recursion, fun stuff. So then if we look at the other one, right, with short float double int, what matches? Third, and now you said false? No, third. Yeah, it's still third. So again, variadic template packs can have 0 elements, so it would still match the third, and then it would match false. Right? So then it would match the first. Alright. So, that's how this works. Is it clear to everyone? Cool. I'm glad to hear it. Moving on, we have still a bunch more, so. Here we have this type, append type unique. Now basically, it might have changed the name, but basically it should append the type if it's not already in the list. So it will append the type, but it will make sure the type remains unique. So basically, for the first one, right, we say double. Well, that's so we're trying to add a double and an int to the list, right? So in the first case, double is not already in the list, so we'll add it. And in the second case, right, int was already in the list, so we won't add it. Right? You see that? So this is a hard thing to implement. How would you implement this? If this were regular code, how would you implement this? Like adding an item to basically a vector if it wasn't already in that vector.
Check each argument against each other argument.
Yeah, that would be one way, right? But you only have one input argument, so you just check the input argument. You check if it's in the list, If it's in the list, then you don't do anything, right? And if it's not on the list, then you add it. We can literally do the same thing with templates here. It's not that hard. Let's take a look. So we have append type unique. It again takes the first type is the type we're trying to append, and then we have the type list, a bunch of types. And we just have std conditional, which is basically a ternary operator at compile time. So like an if-else. So the first thing we can use, right, first up, as a condition, we set the contains type that we just wrote before. So we check, does this list contain this type t? Now if it contains that type t, right, we don't do anything, we just return the type we had, the list of types we had. Now if it doesn't contain this type, then we add it at the end. Right? Does this make sense? And you can start to see like how you can combine things to like build up more advanced algorithms and more advanced behavior, even though we're actually still dealing with literally a type that just has a bunch of types in it, just a list of types. Right? So then, question.
Don't know if you were going to say, but instead of the search, obviously asserting, but you're somehow also appending them or something?
No, we're just like, so the assertion is to check if they're the same, right? So you gotta realize at compile time.
I know that that asserting is checking if it's
True.
And you're checking if they are the same, but you're checking if type list is the same as the.
Yeah. So everything at compile time.
Appending to the type list or something. Or?
Yeah, like everything at compile time, right, is basically pure, and pure functions are basically. So when I say append type list type unique, right? I'm not actually taking a list that actually already exists and changing it. What I'm just doing is I'm creating a new list that has one more element to it. So the type list that gets generated from it, this, right, is just a different type. Now, does it make some more sense then? Right, so to clarify, right, we're not actually appending anything to a list, we're just creating a new list which has the extra element. If it wasn't already in the list. Same with concat list, right, we're taking two lists, we're just creating a new list that has all the elements of both those lists. Right? So then, this is the last one, don't worry. So here we have a unique type list. And basically the goal for the unique type list is to turn the type list into a type list with only unique elements. So here we start off, we have this unique type list and we give it a bunch of parameters. So, and it's just going to go over each of them. So for the first one it's going to be int, alright. That's unique, right? That's the first int we see, so we add that to the result. Then bool, that's unique, so we add it to the result. Then bool again. Now we already had a bool, so we don't add it to the result. Right? Then we go double. Double is still unique, so we add that to the result too. We already had an int, so we don't add it. We didn't have a float yet, so we add that. But then after that we've already had a float, so we don't add it. And then double and bool, those were already both in there. Right, so we're taking a list of like a bunch of arbitrary types and we're just taking the unique elements from them. Right? So how to implement this? This is a tricky one. Yes.
How do you exactly implement that? You start with separating int from the rest and then filtering all the ints out and then continue until you reach the next.
Yeah, so okay, so what he said is you take the first element of the list, in this case int, then you look at all the other elements and you basically filter out each type of int, right, you have there, and that way you build a new type. That would be possible, but it would be a lot harder than what we're going to do. If this were regular code, right, basically the way I demonstrate it with this is basically the way we're going to do it. So we're just going to have two lists. Right, the first list we're reading from, and what we do is every time we add the element to the list, to the new list, if it's unique. And we already have a utility which adds an element if it's unique. So basically how you can see, right, we start out with an empty list, and we say, okay, now add the first element from this and add this int to the list if it's unique. So if it's unique, it's going to add it. If it's unique, it's going to add it. If it's unique, it's going to add it, right? And so on, we continue onwards. And then at the end, right, we have recursively iterated over the unique type list completely, and we've ended up with a type list that is just the unique elements from it. Right? So let's take a look at how we can do that in code. So I'm actually going to use the function type reduction for this because I think it's easier than the parser specialization to see. So what we start off with is just the results, like when we only have results in our set. So basically the final result. Right, so the first parameter to this, like first of all the template parameters will be just a variable pack of results. And then the first parameter will be basically the output of this function. That's the resulting type. So that will be the output type list. And the other one is the input type list. So this function is just there for when the input type list is empty. So we have no more types to iterate over. If so, we just return the resulting type. Now, this is the case where we do have still types in our output, in our input list. So we're going to recurse over the input list, right? So first type name is results. Then we have the type name for the first element in the input list, and then the remaining inputs. So we take a type list parameter, which will have the first and remaining parameters. So the compiler can do this type deduction here. Now the return type of this is not going to be pretty, but let's break it down one by one. So first of all, we're getting the decal type of calling ourselves again. So this is the decal type of calling the function recursively. Now what we're going to do is we're going to, as the first parameter, we're going to append our first input element, right, to the list of results we already had. So to the list of any previous results. And that's where we use append type unique. And then we're going to, as the second parameter, as inputs, that's now basically the same input type list, except for the first parameter. So we basically remove one type from the first parameter, and then we call this. Right? And of all that, we take the decal type to get back to the type instead of a value. Alright, and again return just empty. Then the unique type list itself, the alias, well, this will just take any bunch of types. And basically it's just going to call unique type list, so the first one of that, with an empty type list for the results. So results at the start will be an empty type list. And then it will create a type list of all the types as the input. And this is then going to recursively append each element as if it were unique, or basically call append type unique on each of them at compile time. And again, it takes the decal type of that. Right. How is this? Yep. Yeah, it takes a bit to wrap your head around. But you can see how you can like combine in and of itself like rather trivial behaviors to get like something very like kind of complex that runs at compile time. Yes.
How do you practice this?
How do you practice this? You do it a lot. Like the thing about metaprogramming is you need to be confident with C++ templates first. Then if you know templates very well, right, if you look at specializations and you're okay, that's easy stuff, then you start to build up these techniques. But a key point, which is actually on the next slide, which I'll just summarize everything. I'll just answer it then, right? So what we've covered is that traits are a way of extracting or injecting information into types. Right, so we can extract whether something is a pointer, whether something is a function. We can also add pointers. We can add array extents. We can remove all the extents. So we can do just stuff with types. And we can write our own ones. Now, SFINAE can be used to enable overloads or specializations pretty much on arbitrary conditions. You can, if you're willing to go as far, and if you're really that crazy, you can pretty much check any condition you want at compile time. With the standard traits and your own traits that you can write, you can do pretty much anything you can check for. It just gets exponentially harder. Like the more stuff you're checking for, the harder your conditions will be. Right. So the standard will provide you only with the most generic traits. So they have things like is function, is object, but they won't have things like is my specific class or is function pointer. If you want an is function pointer, you first got to check, all right, is it a pointer? And then is it a function after I remove the pointer? Right. That's how you can see if it's a function pointer. Then use policy-based design to make your class more generic. This is kind of what we skipped, simply for time reasons. And then you can write powerful utilities for working with types. So that's kind of like what I tried to demonstrate on the last slide. And you'll see that this type list thing is actually part of the assignment or the exercise. It's provided. You don't have to write it yourself. It's like there, so you can use it as a utility. Now, most importantly, like this sort of stuff, as you can see, it like gets a lot harder than just your average code, right? If you want to like thoroughly make sure that your code is correct, it's a lot harder to think about when your code is like a mess of template metaprogramming. So in general, if you don't have a reason to use it, don't use it. Like use it when there's a good reason to. There are cases where template metaprogramming can literally make your program like a dozen times simpler or a dozen times faster. But they're not every case. Not every, like, it's a very strong hammer, but it doesn't make every problem into a nail. So don't use it everywhere. And then, this is the point I wanted to hit on. Use an existing library. There are metaprogramming libraries out there. Things like Boost HANA, and like the thing like the type list basically is a very crappy version of what they provide you with. They provide you with very well documented, very well tested, better names, more consistent utilities for working with types at compile time. And anytime you're really like doing this sort of stuff, like if you're doing a significant project with metaprogramming, just use a library. It's just much simpler. Right, and then measure your compile times. Now I'm not kidding when I say that this sort of stuff has definitely an impact on compile times. If you think about the algorithmic complexity of a unique type list, that is basically going to be n squared. So if you put like 100 types in there, you're making the compiler do 10,000 instantiations of a class. That is not very quick, right? So this sort of stuff is great, but do measure your compile times. Like don't just go full in on metaprogramming, hoping, yeah, this will be so fast at runtime, and then your compile time takes half an hour for one file. Because that can happen, like this sort of stuff can explode, right? And this is also something you'll see in the next part, where I actually wrote a particle system in metaprogramming. That's actually a separate DLL for the simple reason that I don't have to compile it with the project. I can compile it on its own, and it isn't included in compile time for your main project. So if you're doing like a real full system in metaprogramming, consider doing that, right? And then, wherever reasonably possible, use a static assert. Because sometimes, something that could have been solved by a simple static assert, that you could have checked and actually got a decent error message, has now turned in 150 lines of error message from the compiler, with like nested types, and like you can imagine like if you have a type list of 10 types, right, and that's like on every single line, you just can't really read the error message anymore. So either you gotta like really work through it very slowly to figure out, or if you use a static assert, you avoid the problem. So especially with metaprogramming, I've said this before, use static asserts liberally. Like they're basically your savior from compile errors. They're the tool to fix them. All right. Then moving on to the next example, which is particle systems. A particle system at compile time. I'm going to start off with a demo for this. So, let's see. And now it will like crash. That would be sad. No. So, well, there we go. So basically, it's just a particle system. It can spawn particles. Like it can spawn different types of particles. It can do quite complex things actually. So this whole stuff, right? And all these types for this, they're basically generated at compile time. So that is what we're going to go over. And I'm also going to go over the exercise then, because part of this will be exercise. All right, so that's what we're going to be building. Right? Actually, like the whole launcher and stuff, that you don't have to build that yourself. So we're only going to be concerning ourselves with the particle systems, the emitters, the particle types, and then all the runtime counterparts. So let's start with the most basic thing: a particle and a particle type. This is the most important thing, and this is how we'll represent a particle type and a particle at runtime and compile time. So to clarify, particle types is what we will create at compile time, and particle types will be capable of spawning particles. And those particles will then be updated at runtime. Like, of course, this is like you saw, right? It depends on user input, so you can't do like the entire simulation at compile time. What you want to do is you want to basically generate the function to do the updating. So let's take a look. We start off with the particle type, and the particle type is just a factory for particles. So it defines a particle here using particle equals example particle, and then it has a create function, which takes a random engine, and then a float x and y. And it's basically just going to be like, okay, create this particle at this position, and here's the random engine if you want to generate random numbers. This is basically just your random source. Alright, now that's a type alias. It's just default random engine. So then a particle itself, well, the particle I showed you, the first one, which is like the little sparks flying apart, right? Those have a position, Vx and Vy, a velocity, Vx and Vy, and then they have a life rate, which is just the reciprocal of the lifetime. So if it lives for 2 seconds, this will be 0.5, and then a life progress. And that's basically, life progress will basically be, okay, 0 is it just spawned, 1 is it's dying, like it's almost dead. Then it has an update function, in which it takes the delta seconds, and it just does life progress plus equals life rate times delta seconds, and then it does the position plus the velocity times the seconds that pass, right? Basic moving stuff around based on velocity. Then it has an SLI function, which is just going to return whether life progress is less than 1. So if life progress is 1, the particle is dead. Then it has a position, which is going to return an array of 2 floats, so x and y. And then it has, and it just returns px, py. And then it has a position setter, which takes to an x and a y, and that allows you to actually set the position of a particle. Alright, so that's the interface for a particle. And yeah, then moving back to the particle type. Now the particle type will have a minimum lifetime, a maximum lifetime, a minimum position, a maximum position, a minimum velocity, and a maximum velocity. And inside of the create function, I'm just going to use the random source to create some. I'm just going to create some random distributions that are going to like linearly pick a value for each of these between min and max. So then we create the particle. We just do random position plus the starting position, right, where we want to spawn it at, plus a random and then a random velocity for x and y, and then finally 1 over the random lifetime. Right? Okay. So then the total interface for our particles and our particle types is this. So we have these functions on them, and this is something that you'll need to generate if you do the exercise. So, but first, let's talk about particle types and particle systems. Right, so a particle system is just one simulation of a bunch of particles of some type. In this case, a particle system will be a bunch of emitters. We'll look at that in a second. But first, let's just create one of these example particle types. So what we do here is we create example slow. Now, can we use const extra with this custom type? So we created this example particle type. Can we use it? Can we use const expert with it? He said if the constructor is const expert. Yeah, that's pretty much the requirement. So if your type only has simple types, like fundamental types, like booleans, ints, floats, that sort of stuff, right? In that case, and it has a const expert constructor, then you can use it at compile time with const expert functions and that sort of stuff. Now, in this case, I didn't actually have a constructor, but that's because the compiler saw, all right, all your types are simple types. They all have a default value, so it just generated automatically a const expert constructor for me. So these const expert constructors, you can either write them by hand, and we'll do that a couple of times, or the compiler generates them. But in this case, yeah. So the official terminology for this is anything you can use with const expert is called a literal type. So if you want to know like what the exact requirements are, you can Google literal type and you'll find it. And then the first parameter, right, this is lifetime min, lifetime max. So that's just that. Position min, position max, this is just so that every particle doesn't spawn literally in the same pixel. And then velocity min and velocity max. Right, so this is for the slow particles. Then we have medium and fast ones, and they just have different values. They just like one moves faster, the other moves slower, that sort of stuff. No magic there. Then we create a particle system, and this is where some of the metaprogramming magic happens. So we have this function, create particle system, and as a parameter, it first takes the name of the particle system. So if you saw in the demo, there's a little name on the bottom left of which particle type I'm spawning. That just comes from this. That's just so I know what I'm spawning. It's not really necessary, but it's nice to have. And then it takes a bunch of emitters. Now,
What does the SV stand for?
String view. So if you want to use string view literals, you have to like include the namespace. So you're using namespace to string view literals, and then you can use the SV behind it to get a string view at compile time. Right. But if you leave it off, it just won't compile. So you'll figure it out soon enough. So yeah, emit on def. Okay, so then we have the emitters. Now this shows two types of emitters: emit continuously and emit on def. So emit continuously is it takes a particle type, fast and medium in this case, right? And it takes a particles per second. And basically emit continuously will just like every so much time it will literally just emit one particle. So emit continuously, for example, fast, it will emit 10 fast particles per second, and example medium will emit 5 medium particles per second, right? Then this is wrapped inside a call to emit on def, and emit on def has as first parameter it takes a particle type, and a second parameter takes the amount of stuff it wants to spawn from that type. So in this case I say example slow and free, and then it takes another emitter inside of it, and it's like, okay, if a particle from the emitter that is contained in me dies, if that happens, then I want to spawn it. So basically it will spawn a particle whenever one of these particles above dies, right? And then we have two of these. So if I actually let's see if I can show this on the demo. If you look very closely at the pixels, right, it will first spawn a bunch of particles that fly pretty far, but one of the slower particles that spawn from the middle, once they die, they split up into free particles, and then once one of those free particles dies, it actually seems to just change direction, but what it's actually doing, the original particle died and a new particle spawned in that place. So that's how you get this sort of weird behavior from very simple particle types, just because we have these emitters that actually emit them in very strange ways. Right? Okay, now moving back to the example. So this is what we're going to be building, the create particle system and emitters. So the particle system interface. That's basically a way that we're going to use type erasure. Again, anytime you're transitioning from compile time to runtime world, you want to have some type erasure somewhere. So in this case, I've decided to do the type erasure at the level of particle systems. So a particle system, right, will be a templated class, but it will derive from this base class, which is this. And a particle system just has two functions. It has an update function and a render function, right? And then this will also have a destructor, because correctness and stuff, no memory leaks. So let's implement the API. We have this thing, create particle system here, and it just takes a bunch of emitters and execute string view as a name. Now, I'm just going to defer this whole thing, the implementation of this, to the particle system description class. So when we talk about this system, right, you have particle types and particles. So particle types are the thing that define how a particle behaves, but a particle is actually the thing that's being simulated. So you can see that as the compile time part and the runtime part. Now, the same thing happens for particle systems and emitters. So the particle system description is the compile time part, that's the thing we're generating at compile time, and the particle system is the thing we're actually spawning at runtime. Similarly, we have the emitters. So the emitter descriptions will be the things we have at compile time, and the emitters themselves will be things we spawn at runtime. Right? We need to have multiple emitters at runtime. So, yeah. Now, here, we're creating this particle system description, and we're just passing on a template parameter here, emitters. And we're creating a tuple of emitters with all the emitter values. Now, a tuple is basically a way of generating a struct at compile time. So, if you want to have a struct of, say, an int and a float, right? If you're just typing code, you can just do struct int float. But if you have a variadic type name pack, like we have here, we can't just magically create a struct from that. So subtuple is a utility that actually makes a struct from it. So by using subtuple, what we can do is just have any struct of any amount of types based on these compile time parameters. So this is generating a struct of emitters. And again, we just pass the emitter values. Now a bunch of code, which is emit continuously and emit on def. These are actually, all they do is, again, they just forward their parameters to some struct that's being created. So in the first one we have emitter description continuous, which takes a particle type and a spawn rate. And in the second one we have emitter description on def, which takes a particle type and another emitter inside of it. And so the particle type, the spawn count, and the parent emitter. Right? Alright, then moving on to this. Then we look at the actual implementations of the descriptions. So the particle system description lives in the detail namespace. It has a string view and it has a tuple of emitters at its source. And then it just has a function to retrieve a name and a function to spawn it. Alright? Now the spawn function returns a unique pointer to a particle system. So this is actually where we're creating the particle system at runtime. Right, these are no longer const expr. This is just at runtime. Now what we return is we call spawn impl. Spawn impl is just our own local function. And we have this thing called make index sequence. Now here you see a few new things. So first of all, make index sequence, right? It takes a single template parameter of a size. And what we pass in is we pass size of ... and then the parameter pack. And that's just going to get the amount of elements in the parameter pack. So if this would be a particle system with 2 emitters, this value would just be 2. Right? Then, yes, so this will create what is called an index sequence. And the index sequence basically goes like this, right? It just starts 0, 1, and then a whole bunch till it reaches n minus 2, and then n minus 1. Now, of course, if there's less than, if you don't have like 10 elements, that will not be that many. But so, but this index sequence, right, it just contains all the indices into something like an array. If you would have an array of 5, of size 5, right? Index sequence of 5 would generate index 0, 1, 2, 3, 4. And the reason we use this is because we can use this with function type deduction. So here what we have is we have the spawn impl function, which takes the x, the y, and then it takes the index sequence of indices. Now indices is being deduced here. So now we get a parameter pack of integers that we could expand, and then we get like each integer, and that way we can do some sort of for each on all the tuple elements. In fact, right, that's exactly what we're going to do. And this again will just return a unique pointer to a particle system. Now this is quite a monster. First of all, it's called make unique, so it's going to make something of this type particle system impl with the emitters. Now this is just the type we'll talk about later. This is basically the runtime counterpart of this description. So this is whatever we're spawning at runtime. Now it takes 2 parameters, an x and a y, and then the third parameter, which is the big one, right? It creates a tuple of the runtime parts of the emitters. So emitters colon emitter will give us, actually that's a type that gives us the runtime emitter type. So we'll create a tuple of that. And then it will do std_get indices. Now std_get is the way that you get the nth element of a tuple. So the way you get elements of a tuple is you call std_get with a compile time number. So for example 5. And then you get the 5th element, well technically like the 6th element in that list because it's 0 based, right? So by doing std_get, we get access to the element of the tuple. And then we call spawn on each element. So basically we're iterating over all the tuples, over all the emitters here, and over all the emitter descriptions I should say. So you have all the emitter descriptions and you're just doing, for each emitter description, you call .spawn. And then you stuff the results from that all in a tuple. And let's look at the parameter pack expansion. So emitters is being expanded here, right? So that we get the list of emitters, and then indices is being expanded here. So we basically pass to the constructor of tuple, we pass all the elements that we want to store, all the runtime descriptions of the emitters after spawning them. Right? All right. Then now the emitter descriptions, which are actually simpler. So that helps. So emitters just take a single type, which will be the particle type they spawn. So they store the particle type that they're spawning, right? Those are the properties that they want to spawn, so that sort of stuff. And they have a spawn rate, which is seconds between each spawn, basically. Then emitter.spawn will just create a runtime counterpart of this emitter continuous for this one. And for the other one, right, again, we're just storing the parameters, and spawn, again, just creates a runtime counterpart, which in this case will be emitter on def. Now, the emitter on def is, of course, a bit trickier because it has a parent emitter. So we also call spawn on the parent when we create it. Yeah. So that's basically all the compile time parts done. So all we need to do now is have the runtime counterparts, which is particle system implementation. Now this will store a bunch of data, and the data is just the tuple of those emitters. So this is the runtime emitters. It will store the data, and it will store a position x and y of the particle system. And then it has a value total time, which just keeps track of how many seconds this particle system has been alive for. Then the constructor just assigns these values. Right, so like I said, this is now running at runtime, so this is no longer compile time. But we still have some compile time parts. And then the update function takes a delta time and a random. Now the total time just gets incremented by the delta time.count. So we're just incrementing the total time by how much delta time has passed. And then we do update impl, which is going to be delta time.count random and make index sequence again. So here again we're using an index sequence to do a for each on all the tuple elements. And if you look at update impl, it again takes a single type name parameter, variadic type name parameter of all the indices, and it takes this index sequence as parameter. So it can deduce that. And basically what we're doing is we're just calling update on all the emitters. So all this does is, like, it calls update on each and every emitter. It looks like a lot of code. It is a lot of code for doing something so simple, but it doesn't get very easy when you're working with tuples and variadic type parameters and that sort of stuff. So then there's the render function, which again we'll just call render impl, and render impl again just calls render on every emitter. So this is, yeah. No, because we're declaring them inline in the class. Like if it were free floating functions, then yes, but these are member functions. So no, it doesn't care. And that's like whenever you're doing templates, right? All your stuff lives in headers because you need to know all the information in every translation unit, so to speak, in official terminology. So yeah, so this is the implementation of particle system. All right. Any questions about this? All right, I'm gonna go a bit quicker, I think. So because like the emitter is basically like just the runtime implementation of a particle system. It's not that important. Like it's basically details. But first thing, like a little struct we have, spawn info. That one just contains a random engine, the x and a y. This is all the information we need to spawn a particle. That's because I'll be passing this around in functions and I don't want to type them all the time. So emitter based, it takes a particle type as a type, and then it just has an alias to particles so that we can use particles more easily, and it stores a vector of particles. So these are actually the particles that are being spawned at runtime. Right? Then it has an update function. You may not have seen the maybe unused before, but that's basically you're telling the compiler it's okay if I don't use this parameter, and it won't give you a warning. Now if you were to get a warning for like an unused parameter before, in templates you literally get like a warning that's like 100 lines long, so it's probably better to just put maybe unused there. Now we loop through all the particles, and we're actually looping backwards, so we start at the end of a buffer and then we go to the front, and then we update each particle. We call update on the particles. We check if the particle is now dead. Then what we do is we use some trick where we swap the particle to be the last particle, so we swap the particle with the last particle and then we pop back. So that way we can actually have constant time removal from a vector. So we don't have to like shift other elements. Now this only works if you don't care what the index of a particle is. Now in general in a particle system, you don't care whether your particle is at index 5 or at index 10. So if you actually care about the index of particles, then you wouldn't do this. Now this is a little trick to make that faster. Alright, and then one thing I haven't said before, but we need to have some way to get a callback if a particle dies. So what I do here is I add a template parameter on def, and this is going to be the decal type of some function, default on def. So default on def looks like this. we take a reference to a const particle, and it's just going to do nothing. Right? That's the default behavior. By default, if a particle dies, we don't care. But we can override this with the template parameter and a function parameter. So let's now add an onDef parameter, and we default it to default onDef. And then right before we destroy the particle, we call onDef with a particle. So now we have a way of getting the information of when a particle died. We have a way to basically register a callback. And we'll see how we need that for emitter onDef, which is going to have to emit a new particle when a parent emitter has a dead particle. So, moving on, the spawn particle function. This is relatively simple. It just calls create on the particle type, which is one of the first functions I showed, right? And it's just going to give spawn info.random, spawn info.x, spawn info.y. So it's just going to create a new particle and push it back to the vector. Then render. This is going to iterate over all the particles. We have a bit of new syntax here that have been in the exercises before, but I haven't actually shown it on slides first before. So this is called a structured binding on the line 47, I believe. Yeah, so basically what it is, right? If you remember, position returns an array of two particles, two floats, right? And using the structured binding, I can just, this is called destructure it. So basically what I do is I say, right, I want the first of those array elements to become fx, and the second of these array elements to become fy. I cast it to an int, I check if it's within the screen boundaries, and then I plot it. So yeah, I plot a white pixel there. So that's all the rendering code. It's not really that relevant. So then, emitter continuous will inherit from this emitter base, and I've aliased base so that we can just do base colon to call function on the base. It will have a particle type, a spawn rate, and a spawn count. So emitter continuous then takes a type, the constructor just takes the particle type and it just takes a spawn rate and it stores them. And then if we look at the update function, we see we have this template parameter onDef, which is going to default to the parents onDef, and we have all the same parameters, so total lifetime, delta time, spawn info, and onDef. Right. Then we call the base class update function, so that's going to actually do the logic for the updating all the particles and removing them when they're done. And then we have a spawn target. Spawn target will just be the amount of particles we should have spawned by now. So emit continuously, just emit so many particles per second, and it's just like it calculates how many particles should I have spawned by now. And then while the actual spawn amount of particles is less than how many we should have spawned, right? It's going to spawn extra particles. So it just increments spawn count and it spawns an extra particle. Right? That's the update for an emitter that's continuous. And that's it. Then the emitter onDef, and this is, I believe, the last one, right? This will have a particle type again, a spawn count, and a parent emitter. And it again has a constructor which literally just stores those values, does nothing fancy. And then we have the update function, which again takes total time, delta time, spawn info, and onDef. This time, first we're going to update our own particle system, right, our own emitter, and then we're going to call update on the parent emitter. And here we get something that's a bit different, right? We have a lambda function, right, a lambda, and it actually has a capture this time. So the thing in the square brackets beforehand, that means you want to be able to access variables by reference here. So we don't want to make copies of the variables, but we still want to be able to access them. And then basically what we can do is we can iterate for I to spawn count, right? And for each particle there, we get the position of the particle that died. We spawn a new particle at the position of the particle that died, right? And then we have the render function, which is going to call the render on the parent emitter, and then call our own render function. And that's pretty much it. That's how the whole particle system and emitter stuff works. It's quite a bit to go through. But to summarize, right, what we've implemented now is a compile time description object of particles, emitters, and particle systems. We've run some instantiation of all those counterparts, the actual logic and rendering of the particles, then the usage of std_tuple and the make index sequence, how you can iterate through a tuple, more type erasure with the particle system that we implemented, and then how you can use functions as parameters, so higher order functions, as the official terminology calls it. How about the rest? Well, this is actually like how I define the fire particle. So if you remember back to the demo, we had fire particles. This is how I define them. I have this create particle type. And I say, all right, the lifetime must be some random value between 0.2 seconds and 0.8. I say velocity, position must be between -2 and -2 and +2. Velocity must be random between -4 and 4, so a little bit of horizontal velocity. And vertical velocity must be a random value between 0 and 50. So it's going to be moving up. Right. Then I, for example, had the fireworks, which had 2 parts to it. So in this case we have the fireworks rocket, which is just going to be fired up. Now the velocity here is the most interesting part, right? It's going to use polar coordinates. So that's basically, instead of giving it an x and a y, what I give it is a direction and a distance. So the first 2 parameters there are minimum distance and maximum distance. And the second one is the angle. So pi times 0.45, you know, that's radians, so it's like between here and here, you know, so it's like a little cone in which it will emit the rocket. And then it has some downwards acceleration for gravity. And the particle explosions, right? They, again, their velocity will be a polar coordinate. So that basically created this ring that you saw, where all the particles of the explosion will be within that ring. Now, the system for this is actually pretty simple. So we have the fireworks. We continuously emit a firework rocket. So every, we emit like 0.75 rockets per second. And then when it dies, we spawn 100 new particles. So we spawn 100 explosion particles. And that's how the firework was created. Now, implementing this stuff, that's the exercise for this week. Right? I will be providing the solution as well. Like I just bundled everything this time. So if you want to work on it, but you get confused very easily, you know, it's there as a reference. It's not trivial. It's without a doubt the hardest exercise, but then again, this is without a doubt the hardest topic we've covered. And yeah, so your goal is basically, you know, you create these this create particle type function, and you generate the particle type and the particle class for it. Yes.
How long did it take you to do this?
The particle type part?
Yeah.
2 hours.
And the entire particle system?
The particle system, so the particle system with emitters took me, I would say, another 2 hours.
And to understand this?
To understand this, I mean, like, 3 years. Like, for however long I've been doing C++, well, it depends, you know, it's just your knowledge of C++. It's, like, with the type list that is provided, and some of the utilities on it, right, it's actually, it seems a lot harder than it is. But, yeah, so all the techniques that are required to implement it are in the slides. And if you want to make your life a lot easier, if you like actually want to undertake this exercise, right, you do a bit of upfront planning. So you think about, okay, how do I actually want to start generating these things? You look at the examples I gave you of like all the particle types, right, and then you decide it. So if I actually bring up the exercise here, it's an exercise particles source particle simulation. So this is the example we actually saw, right? This is the example particle and the example particle type. So these have the APIs that you need to generate on them. So you need to create this create function, and you need to create the position and is alive and update functions. And basically here you have all the particle types I had defined, all of these, and all of these registrations here, which I haven't shown this part, but basically there's another layer on top of this which does basically the DLL stuff, which I haven't shown. But that's already made, so you just got to add the particle systems here and then it will work. Now, yeah, so basically your goal is like be able to uncomment this and then compile and actually run. And if you can do that, well then particle solution solved. So if I run it without solving it, right, I'll just have the single particle type, which is, you can see at the bottom, right, it's just this one. So this is the one you already have at this point. This is what you start with. So you don't have to build anything from scratch, right? This is what you start with, you just have to do the particle type stuff. Alright. And if there are no questions, that should be it. Question? How much is sped up? No, I've never like done a runtime version of it. I have tested performance. I ran, I believe it was 50,000 particles, and I couldn't notice a difference in performance at all between no particles and 50,000. But it's definitely, so I didn't optimization was not the primary goal of this, right? This was mostly just as an exercise. Because the stuff with like the way I spawn particles and the way I manage their lifetime, you're just putting in a std vector. It's not extremely efficient in terms of memory and that sort of stuff. But basically, if I unlock the FPS on the example, right? You know, it's like it's running at 1 to 3,000 FPS and it's fluctuating like mad. And basically, when I start spawning, actually I'm in debug mode now. So when I start spawning, oh no, sorry, this is the Reese build. So if I start spawning stuff, like I couldn't really notice any like dip in performance. So I don't know. Performance was adequate. So that's all I can say. And then, you know, whatever. Lots of stuff. Anyway, yeah, that's it. All right, question?
What other practical uses do you think
For particles or for metaprogramming?
Yeah.
There is too many uses. There's what are some good examples of it in practice? Well, basically inside of an engine, right? Asset systems, things like that. So you have different asset types, and you use them with metaprogramming. But basically, anything you can do with a runtime system, you could probably do with a compile time system. So in general, like I said, you don't use metaprogramming unless you actually have a reason to do it, and a reason might be performance. A reason might also be flexibility of your source code, so or syntax basically, right? So if you look at std vector is pretty convenient for usage, right? If you have a runtime counterpart to that system, right? For example, C has some utilities to create a list of that too, right? You're basically always calling functions with void pointers and all that sort of stuff, and that's just not a nice API to have. In addition, SFINAE you can use to change the behavior of your function depending on what parameters you take. So an example of this in the actual framework that you get with it that does like the rendering and stuff is that there's a function called fill on a surface, and it can either take a lambda that just takes an x and a y position and then you return a color. So basically it fills every pixel of the surface depending with just an x and a y, or you can take 3 parameters, an x and a y and a previous color, and you can actually modify the color. So depending on what you pass it in as parameters, you can actually have a different output. So there's a lot of uses for this. It's just not always is it worth using this tool over others because of the complexity involved. It can load, well, if you like, okay, so if you build an entire system like this in with metaprogramming first, then it might load your compile time. But if you do it like the entire standard library, right, is built with templates. There's a reason it's called the standard template library. So it's not that templates per se load your compile time. It's when you're doing too much of it, basically, or when you're doing when you're dealing with too much data. Like I said, for example, the type list, right? If you have 10 types, it's not a problem. If you have 100 types and you're doing an n-squared algorithm, you suddenly went from 100 instantiations to 10,000 instantiations. So it's mostly just look at the complexity of the algorithms you're using. That's also why I recommend you just use a library for it, because these libraries have been optimized for compile time. So they're still not, obviously, like they're not going to be super fast, but they're going to use smarter algorithms. For example, they might use a binary search instead of just a linear search, which is obviously a lot harder to implement, but it's faster. So yeah, that's pretty much the answer to that. Any other questions?